In this problem, we'll treat a collection of faces as a set of vectors in a high-dimensional vector space, and we'll look to represent this space as well as we can using a much lower-dimensional vector space. First, recall that the singular value decomposition is a tool for representing a collection of points as well as possible. We learned that the line spanned by the first column of U minimizes the sum of squared distances from the line to the points represented by the columns of A. Similarly, the k-dimensional vector space, which minimizes the sum of squared distances to a set of points in Rn, is the span of the first k columns of the U matrix in the singular value decomposition of the matrix obtained by arranging the coordinates of the points as columns in a matrix. Each pixel in a grayscale image is represented by a real number between 0 and 1, which indicates how dark the pixel should be. So we need mn real numbers to represent an m by n photo. In other words, we can think of an m by n grayscale image as a vector in an mn dimensional space. To make an image into a vector, we just need to order the pixels, also known as serializing the image. We will do this by going down the first column, then down the second column, and so on. So in the Yale face database we're working with, we have 165 vectors in R to the 4045. To approximate these faces as well as possible with a small number of vectors, we arrange them into a 45,045 by 165 matrix, find its singular value decomposition, and select the first so many columns of U. Here's what the first column of U looks like, with the pixels rearranged back into a rectangle. This is the vector which best approximates all of the photos in the database, in the sense that the sum of squared distances from each image to the nearest multiple of this one is as small as possible. Similarly, if we take the span of the first 5 columns of U, then we have 5 vectors whose linear combinations can approximate the 165 images as well as possible. In other words, we can think of the columns of U as face ingredients, which can be combined in different proportions to form specific individual faces. To see this in action, we use the following fact from linear algebra. If W is a matrix with orthonormal columns, then WW prime is the matrix which projects onto the span of the columns of W. In other words, the entries of W prime V tell us the weights to use in forming a linear combination of the columns of W, which approximates V as well as possible. We can calculate W times W transpose V, where W is the first k columns of U, and adjust k to see how the individual face is approximated increasingly well as k increases. The columns of U are called eigenfaces, and the spans of the first several eigenfaces are called face spaces. This scheme was developed by Surovich and Kirby in 1987, and it's useful for both facial recognition and storage. For example, we can check whether a region in an image contains a face by checking its distance to a face space, and we can store a large number of vectors in a database by storing their eigenface coefficients rather than all of their pixels. The most common convention is that U and V prime are both square orthogonal matrices, and the rectangular matrix in the product is sigma. However, we can observe that if A is non-square, then sigma necessarily has a rectangular block of zeros on the side or bottom. Suppose that m is greater than n, for example. Then we can write sigma in block form as sigma 1, 0, where sigma 1 contains the top n rows and 0 represents the last m minus n rows. We can also write U in block form as U1, U2, where U1 is the first n columns and U2 is the remaining m minus n columns. Then multiplying out this product, we get that A is also equal to U1 times sigma 1 times V transpose. In this product, U1 still has orthonormal columns, but it isn't an orthogonal matrix anymore since it isn't square. A similar analysis applies if n is greater than m, except that V is the one which is non-square in that case. Conversely, given a factorization of the form U1 sigma 1 V transpose, where U1 is rectangular and sigma 1 is square, we can recover the full SVD by filling in rows of zeros under sigma and attaching further orthonormal columns to the side of U1. This is possible since we can extend the columns of U to a basis of Rm and apply Gram-Schmidt to make the whole list of columns orthogonal. In the composition U times sigma times V transpose and U do not alter the lengths of vectors they are applied to. Therefore, the factor by which a vector V's length is stretched by this composition is equal to the factor by which sigma stretches the vector it is applied to. Since sigma is diagonal, the vectors it stretches the most are the ones which have a non-zero entry in the position of sigma's largest diagonal element, and zeros everywhere else. If sigma's diagonal entries are arranged in decreasing order, then the unit vector which is stretched the most is the one that V transpose maps to the first standard basis vector. In other words, the vector that V transposes inverse maps the first standard basis vector 2. Since V is orthogonal, its transpose's inverse is itself. Therefore, the vector which is stretched the most is the first column of V. This vector maps to the leading singular value times the first column of U. In this problem, we're asked to establish the product rule for differentiation of matrices whose entries depend on a single real parameter. First, let's check that this rule works on an example. To show that two matrices are equal, we can show that all the corresponding entries of the two matrices are equal. Let's just take the top left entry as an example. Others will work similarly. The top left entry on the left-hand side is equal to the derivative of the dot product of the first row of A and the first column of B. We can apply the ordinary product rule to each term in this product, and we find that we can repackage the resulting expression as the sum of the dot product of the derivative of the first column of A and the first row of B, and the dot product of the first column of A and the derivative of the first row of B. This is the top left entry on the right-hand side of the equation.